Let me say welcome again to How to Design Electronics. So this is season 2, and we've got one more this season, which we'll talk about at the end. As I've mentioned many a time, really these sort of hour sessions are really about sharing ideas. I've been doing this now for nearly 30 years, and I've picked up a few tips and tricks along the way, and that's just what I want to share with you all, really. So it's just top tips. So it isn't a bit of a whirlwind tour. I usually have sort of 4 or 5 related topics, like topics in chapters in a book. You know, you turn to the next chapter and it's on a slightly different subject, but still related to what we're talking about. So that's kind of the formats. I've got a few slides, not many this evening, but they are all available to download. So I'll share that with you now. So if you do want to download anything that I put on up for us to look at, if you hop on over to my website, siliconcortex.uk, and scroll down to what looks like this downloads, you'll see it'll say how to design electronics, and season 1 last year, you can download all of those, and season 2, which is what we're doing at the moment, you can download all of those. There's a sneak preview into season 3 that I'm starting to think about, and I'd love to have a chat hopefully toward the end where we can talk about all of that. Oh, my computer's turned off there. Right, yeah, so the biggest problem I have in all of this is my computer has a tendency to either drop the Wi-Fi link, which is never good, or we start to lose the resolution. So if you drop the Wi-Fi link, it might take me a few seconds before I've realized and I have to reconnect, and my graphics look absolutely brilliant. And if they go crazy on your screen, then you really need to tell me, otherwise I really won't know. Okay, right. I think they call that housekeeping, don't they? So, tell you what, we're going to be looking at debugging electronics today. So, I thought we'd start off with a few little simple things that put onto electronics, and then after that, we'll start to drill down a little bit into a few tools. And I've got a few with me all hooked up, which hopefully will work. I've got desk cam today. So hopefully we'll be able to move desk cam around and have a few things on the bench here for us. So here we go, LEDs, right. So whenever I'm developing electronics, there's a board here. I pulled this one out the drawer about half an hour ago. I always put LEDs on any microcontroller. It's dead easy to do. I always, when I first bit of code is I always just do a simple light sequence, just so I know the LEDs work, just so I know my program is up and running and it hasn't hung. And of course, I also tend to use LEDs almost like a watchdog. So maybe at the end of the program, I might have an interrupt before it goes back to the beginning of the program, just to blink an LED, just so I know it hasn't hung in real time. Because if we're doing things like, the Arduinos and, embeds, for the ARM stuff, there's precious little in there to tell you whether your code is going to hang or not. So I always put LEDs on my boards. And there's 2 ways you can do that. You can either do it as like a source, which is very simple. I just put a resistor in there. This is, say, a 3.3 volts circuit. So this is current source, just turn the LED on, nothing amazing there. Or you could do it the other way around, of course. You can just have it sync in the current. So obviously I put an N in the front, just so I know it's active low. You can put an exclamation mark in front. That's another way of just indicating it. Or you can put a bar over the top. Now, I tend to avoid a bar over the top when I'm drawing schematics, because what I tend to find happens when you bunch things up, you sometimes, this bar above gets lost in another graphic. So if I move that up there, the bar over it would actually end up being on the line and I just wouldn't see it. So I tend to use the letter N in front. And then my code and the schematic then tie up. a lot easier, so I can see what's going on. The other thing to bear in mind with either a current sink, as this one is, as opposed to a current source, which this one is generally you can sink a lot more current than what you can source. So that's just another thing just to bear in mind. So I usually put, 3 or 4 on a board, and I've always found it extremely useful. So I know in a bit of code, I put a light on, I know what bit of the code it's got to. So it's also a good way of trapping errors, that if it's hanging somewhere in your code, just using an LED, that if the LED doesn't come on or doesn't go off, you've got a really good idea where in real time your code has hung. So top tip, I always put LEDs on boards. The other thing I always put on my boards is, of course, switches. Always a good idea. So again, I use this quite a bit for debugging. If I want to just pause my code somewhere in real time and wait until I've pressed a button before it carries on, that's another great way of debugging. This is called debouncing. The not often a way you'll see a lot of LED circuits. I'm going to draw it here because it's not on here. Let's say it's plus 3V3. Another way you'll often see a circuit drawn for a switch, of course. There we go, and that's going into the processor. It's just to do a simple circuit like that. Now, there's nothing wrong with that, you might say. That would work. But don't forget that when a switch contact closes, it doesn't just close and that's it. When it closes, it will what's called bounce. It's a mechanical bouncing around. Relays do it as well. So what you'd find would happen if you just didn't have any debounce is you'll just see, if you looked on the oscilloscope, it would see, you'll probably see lots of ons and offs. And trust me, if you're trying to trap an error, that's probably not a good thing. So, whereas if you use a nice debounce, you'll see it'll just nicely switch on like that. I hope you see that okay, everybody. It'll just easily, nicely just switch on and you won't have any problem. So I use this circuit a heck of a lot. It's on this board, debounce. Of course, you can do it in code. But if you're just using a simple error trapping for debugging, why do you want to go to the trouble of doing lots of debounce in code? You don't, you just want to have something very simple in electronics.
Stephen?
Yep.
2 questions. First is, why the extra resistor in your printed case rather than the simple one? And the second is...
this one.
Yeah. Well, actually, Wibble. So the second isn't so much a question as a statement. If you're going to do software debounce, that takes the form of basically sampling the input line lots of times over a period of something like a millisecond.
Yeah.
And waiting until you get a fairly consistent output from that process. So, if you get far more ones than zeros, then decide that it's a 1.
Okay. Okay, to answer the second question first. If you're just trying to do some simple debugging and you haven't got a lot of memory, do you really want to take time? So you could do this in basically one line of code. So it's just about making your life easy.
No, I just wanted to explain what software debounce meant, and also to point out that if you're relying on an interrupt in your input key to signal that something changed, then software debounce is not what you want, because you will end up with lots and lots and lots of interrupts, which will be really irritating. So that's a very good reason for going with the capacitor option. Now I will stop chattering and let you talk about the resistor.
So so the point of these resistors is it's just to smooth it. So when you switch it, when you press that in, it'll discharge that way. The capacitor, the charge capacitor will discharge that way. and you'll get a nice smooth off. And then when you release it, I've got it, there we go. When you release it, obviously the current will just flow that way. So by having these two resistors, I mean, it's, let's say the point of the two resistors is just so you don't see switch bounce in either going high or going low.
Ah, understood. Thanks.
Yeah, because you wouldn't want it in either event, really, would you? Okay, good question. I encourage questions. I encourage interruptions. They're always good. Right. Okay. So as I say, these are a little whirlwind tour. So let me move on to something slightly different for us. And something else I use in debugging quite a lot is the UART. This is on every single microcontroller. You know, the Raspberry Pi's got them, the Pico's got them. I've got one here. So what I tend to do is, and here's one I prepared earlier. Is it that way? Almost might be that one as well, isn't it? Look, I think it is that one. How handy is that? These are coming quite difficult to get hold of now. But what I have done is I've checked up on Farnell. This is their magic Farnell number, and this is the cost. I think you have to add VAT to that. And you can just connect this to the UART port on your device. And I've got a demo here, so I'm hoping this is going to work for us. And then it's a great way of just having data pop up on the screen. And I do have here the data sheet as well. I just grabbed a couple of pages just to give you an idea of this particular one here. Hopefully this laptop won't keep turning off. It's meant for it to go, oh, I'm back on. There we go, hopefully. Right, okay. So, buying these chips is pretty hard these days, which is why I think the way to solve the lack of chips on the market is to go modular if you can. So I would, whereas I used to, and you still can if you can get hold of them. So this is the very simple schematic. This is the chip, which is this black blob here. This is the USB end, and a bit of filtering, and then they've got the UART. I'm sure you can read that. It says TX and RX, which would go off to your microcontroller. So I've got a demo just here, which I'm hoping if I just go to camera gymnastics, I just go to camera, Orky camera 1, I hope. Yes, that was amazing. Right, so I've got here, this is my little board, in fact, camera gymnastics part 1. There we go. So here's my little board. I'll just show you what I've got hooked up to it. Right, so this is my microcontroller in the middle. And then this is the UART chip in a different package to what we've got here, but it's pretty much the same. And then I've just got it going straight to USB. So it's a UART to USB interface chip, just a chip, there's no magic. And then that goes straight into the UART of your laptop or your computer, of course. And then here's the first Wizzo. So what I tend to do when I'm debugging, I'm not sure how in focus that is, but we'll get the general idea. So what I do, whenever I've got these debug ports, hopefully this will work. If I do that and press open, fingers crossed, if I hit clear, first thing I have pop up on the screen, there you go, that worked. I'll try that again, and then hopefully I can capture it there. So to know my UART port is going to work, so there's no point just having a UART and just waiting for something to pop up. I always put a little debug message in. So as soon as my microcontroller starts up, I've got a little routine that just squirts anything to the screen, your name, hello world, what it is you're tinkering with, and then you know for your debug that the UART is working. And just by way of example here, this is some work I've been doing. I just grabbed this one out the drawer. obviously I have my name and I actually read out, it says hardware. This is actually the serial number of the actual silicon. So a lot of this is a text field that I create, and then I actually just read something from the chip. That way I know that my UART port is working perfectly.
Stephen?
Yep.
Apologies for another interruption, but you did say.
Yeah, I did.
One thing to note, if you're using a proper hardware serial port rather than something bit banged or whatever, make sure that you disable hardware flow control, or you will have very mysterious lockups and no output.
Yeah. Then there's a number you can use. So this is real term, which I've used quite a bit. Yeah. Putty is another one. And certainly for this AI stuff I'm doing, I can squirt it out. And of course, something like Putty, I'm not sure if I think you can do it in real term as well, but certainly in Putty, P-U-T-T-Y, you can actually send everything to like a CSV data file. So for example, I mean, I haven't exactly got it running, but just to give you an idea, is I've got a load of data there streaming up the screen from something or other. And so that could easily be just sent to a CSV file. And what I'll often do is I'll put all the commas in and everything, and then I can just load that into Excel, comma delimit, and then I can just sort of just check everything's working okay. And I actually do that. Certainly with the AI stuff I'm doing, it's a great way of just validating that, is this reading correctly? And of course, make sure that, if you've got any maths going on, it's a great way of then checking that the maths are all correct, because you can just sort of do it pictorially in Excel. And I tell you, I've been spending the last 2 weeks doing some EMC work, and the amount of people I see there, whenever they've got data streaming off a product that they're testing, they're always using real-term or Putty or any of these other very simple UART interfaces. So you don't need anything fancy, and well, it takes hardly any electronics and next to no memory, which is always a good thing. Right, okay, anything else on that? Oh yeah, just one other thing I will mention. So a lot of these devices are, like if you're using an Arduino, for example, it'll be 5 volts. But a lot of these modules might only be, say, 3v3, a lot of these little tiny chips. So usually the chip, you can put 5 volts into them, it's not a problem. And of course, if you've got a 3v3 circuit and a 5 volts UART module, if you're just doing TX, chances are it'll be a sufficient voltage level not to worry too much about it. I've never had a problem, if I'm honest with you. Anyway, right, okay, let's have a look at another really useful tool. So what have we got here? Oh yes. Right, let's go back to gymnastics of camera for a second. Dizzy. Right, where are we? So let's just uncamera that. Back to there. Right, so this is all going amazingly well so far. Right, let's just turn the light up a little bit. Right, a few other little tools here for debugging. I've got them here, and we're going to have a play with one of them in a moment with their Raspberry Pi. I've got one of those out. So these are other uber-duper nice, cheap and cheerful tools. If you type Logic Analyzer Saley into eBay, you can see these, what looks like a small box of matches. We're going to have a tinker with that in just a second. I'll show you that as a really useful tool for debugging. And another one, of course, is a logic probe, which I've got one here for many, many years. And we'll have a tinker with that with a Raspberry Pi in just a moment. But there we go. Slightly more expensive at £55. But we'll have a play with that on a Raspberry Pi in just a second, so you can see how that one works. But just for this one here, what I have hopefully set up, and we'll fingers crossed this will work. Maybe we'll try it. Is going back to here, this one here. I've set up for us the UART, which is on here. This is an example of a Chinesium job, which you can get for a few quid off eBay. And all I've done here, I've just connected a common ground. It's always a good idea. And then there are just some data pins here. And then if I just change to a different camera, fingers crossed, this will work again. Right, here we go. Right, camera gymnastics coming up. There we go. So this is that's not in focus, is it? Right, you'll get the idea. So this is a very simple program. You can download this for free. It's saying disconnected there, which is not really what I wanted to see. I told you anything could happen when you're doing this. It's saying disconnected. Right, let's see if I can reconnect it. Well, everybody. Right. Okay, it's saying disconnected. So just before we get carried away with that, we'll try and make it do a demo. You have up to, with these Saley devices, you have up to 8 inputs, and you can do all sorts of things. Analyzers on here. If I just hit analyzers, and if I do show all, I might have to read them too, because you can't read that at all, can you? That's just a white screen, isn't it, to you lot? Right. Yeah. Okay. I will have to tell you what it says. Yeah. Okay. It is great here. I could do the camera that has much better focusing. Right. Okay. I can tell you, you can do debugging with things like I2C, which is a good idea, SPI, one wire, CAN bus. I'm just reading these off here. I2S, which is for audio. It's got Manchester encoding, which of course is, I think, Ethernet, if I remember right. You can do SWD for programming chips. You can do JTAG. You can obviously do standard GPIO. And of course, you can do UART. Now, what I've got on here, which is really nice, is, so I've just, oh, hang on. There we go. So just by way of example here for us. So I've got a load of data here, which I've captured earlier, just coming in over the UART. And then it'll decode for you and tell you, if I just zoom in, and you might just take my word for this, that what it says. It'll actually decode the actual data that you've got coming in, and it'll tell you exactly what it is that you've sent. So if you're sending, say, some AT&T commands, which is what we've got here, and you're maybe sending the wrong AT&T command, and your module's not working. So this will just very easily tell you, oh, what is the data that you're sending? And then, hey, yeah, you can see exactly that. Maybe you're sending the wrong command. Or I was working on a project many years ago now, we was using this, and the customer reported they didn't have a SPI running at all properly. So we just connected this up, and it's very obvious that, that the clock on the SPI wasn't running properly. So it's a great tool for debugging electronics of things like I2C, SPI, UART. Certainly with the I2C, which is address-based, you can see with these sort of tools exactly what the address is you're sending, and are you getting an acknowledgement back from the device. So then you'll know, okay, I'm just clearly got the wrong address, or the chip's not working properly. So highly recommend you treat yourself to one of these. Right, okay. Tell you what, because I've got out of the drawer for us I can unplug this. I think unplug that, move that to one side. Camera gymnastics. Right. So I've got for us a Raspberry Pi board here. And what I thought we could do, we could just use a logic analyzer just to probe it. I'm not sure if we've got one of these that makes space or not. That might be an idea if we get one. Right, so I've got some power here on this, oh, hang on, this lead. There we go, hope you can see that. So I'm just going to power this up. There we go, the lights are on. And then I'm just going to connect some power to my logic probe. There we go. And then this is just an easy way just to probe a board. So hopefully this will work. So you can just probe different parts of your board and just see what's happening. So for example, I'm just going to stick it anywhere. There we go. That's green. That's on. So that's logic low. Logic low that side. There's the logic high. So actually, this is actually just a capacitor I'm probing here. So it's probably not an enormous surprise that that's the positive side, and of course that's the negative side. For other areas, I mean, I have no idea what I'm probing on here. I think if I probe here, you see, I've got a flashing light. I don't know why it's pulsing. Maybe if I've got the schematic out, I might be able to find out. But if this is something which you've designed, you could just go around and probe it all and work out what you've done wrong. Easy peasy tools that aren't expensive. Right, the last thing I've got here, and this is way cool. This is something which I actually built this. It's on the other camera. I actually built the last bit I wanted to share with you last week. So I've been doing a lot of stuff at EMC recently. And I know it's a bit of a tear-jerking price. But not all your problems are going to be down to the fact you've just wired the thing up wrong, or you got your code wrong. Some problems are caused by radio interference. And this comes down to how well have you designed your electronics. And of course, if you're designing things like, like Raspberry Pis, for example, you've really got to understand RF, how to suppress RF problems. Because if you have problems with noise, it could be completely messing up your electronics and you just won't understand what's going on. Now, I've got a slightly more expensive tool. I've got the one on the right here. I'm going to go to the other camera in a second. But there are cheap alternatives. I got told this one here, it's a pocket-sized one. I think it's about the size of a Raspberry Pi. You can just go onto Analyzer. I think that's the American spelling. If you type in Analyzer and just copy that into Amazon, you'll see these pop up here for about £72. The one we're going to play with is about £4,000. So maybe not hobbyist, but extremely useful. So let's just rotate the camera and see if this amazing, no, which camera is that? That's not a camera I want to be. Is that one? It is. Hi. Here we go. Right, table gymnastics. So I've got here an actual analyzer. So that's what this thing here is. When we're designing electronics, we're usually, as long as there's no Bluetooth or Wi-Fi, we'll be looking for problems in the 30 megahertz to 1 gigahertz. If you've got Bluetooth, as you do on a Raspberry Pi and a lot of wearable electronics, which is 2.4 gig, you're going to have to go up to 6 gigs worth of looking for problems. And interestingly, because battery products are usually very small, you tend to start to see the problems at the very high frequencies. And certainly in the project I've been working on for the last few weeks, it's a very small wearable device with Bluetooth. And we had problems up at the 4 to 6 gigahertz region. And that's not uncommon. So what we can do with this is, I've got here, hopefully, I'm hoping this is going to work really well for us. Right, so I've got in here as well a number, and these will work also with that cheaper analyzer. I've got here some different size, they're called search coils. They're just PCBs with a bit of heat shrink and a small, what's called an SMA connector. That's all it is. Plugged into the top. There we go, plugged into the top here. I've got just a cable coming off, goes around here and then plugs into here. And then I'm going to go around the board, and we'll do this in a second, and we'll see which parts of the Raspberry Pi are noisy. And I did this half hour ago, and it did work. And so this screen here, just so you know, I've got frequency going from 30 meg here up to 1 gigahertz. And I've got a dB range in this axis. What the range is in the vertical axis, probably don't worry too much about it. You're just looking for a problem. And if you've been to an EMC test site and you know you've got a problem in a certain area, then you can use that as a reference to try and sort it out when you get back to the office. So what I'm going to do, interestingly, I'm not sure if we can track, if I can do, I'm going to try this. If I have that there, bring that up there and hold it. If I move this coil around, we might see some problems on the Raspberry Pi. So the search coil in the middle of the little ring is the, okay, there's a little bit of stuff going on there. There we go. So there's a bit of stuff going on there in the Bluetooth module. This is the Broadcom chip. It's reasonably quiet, isn't it? It's not too bad at all. There's a little bit there, just there. I don't know what that one is. It's not too bad. I think over here, things start to get a little bit more noisy. Look at that. So the question is, and this is where you plug in your USB, is there a potential for having noise come straight out of the USB and causing you a problem somewhere?
Stephen?
Yeah.
I happen to know, because it's been a problem for Pi users in the past, that the problem there is the power management IC is noisy. So it's not the USB input, it's the actual circuit there. So what you're looking at is the actual power supply.
Yeah. So it's interesting. So you know, it's a problem with that. So we've proved it here that so the search coil is right over the inductor, and of course that is singing like an absolute canary. So so you're absolutely right, Reece. Look at that. So all over this area around here, which is the power management, that is where it's super noisy. So that could be hushed up. That wouldn't be too difficult to quieten up. And you don't need to use fancy church. We'll talk about it more next time, of course. You know, a 0.1 penny capacitor in the right place can make a world of difference to a board.
Just out of curiosity, the littlest thing with a heatsink, that's the USB, PCIe to USB converter.
Yeah, that's not too noisy, but I have to say, it's clearly all around here. Now, of course, it works, and obviously, if you pass EMC, who cares? But of course, as I've discovered in the last week, CE plus CE does not equal CE. You can be very close to the limit, and then completely fail CE because you're adding something else to it, and then you're just the wrong side of the fence. What else was I going to share with you about that? Oh yeah, it's also another, I mean, something like this or the other analyzer, which you get for £72. These probes here, which I've bought, I bought these arrived a couple of weeks ago, and I think they just cost me £20 for the set. So absolutely cheapest chips. And yeah, look, so there's a problem. The other thing which you can do for debugging is inject noise. And this is something I learned a couple of weeks ago. I'm hoping this is going to work. So what I've got, if I just zoom out a little bit, here we go. So you can see everything. And this is the last bit. Right, so just turn this on. So this what I've got here, this is actually a RF signal generator. That, and of course you can't see what the screen says. That'll generate up to, I think, goes from like 10 kilohertz up to 1 gigahertz. No, well, it might be 1 megahertz. But anyway, if you know you've got a problem from your EMC work, all I've got here, so plugged into here, I've got a cable. And then all I've got in here, I've got a drawing of it somewhere. And I'm just drawing up. Let's have a look. Here we go. Here's the drawing. Here we go. I can hold it up for you. So I've got a signal generator, not necessarily the one here. They're not cheap, unfortunately. So you need to find someone who's got one. And then all I've just got a 10 nanofarad capacitor going to a probe tip. And so I sacrificed a multimeter lead for this exercise. And then in here, I've got my capacitor, which is just straddled by 2 popsicle sticks, so it didn't keep breaking. And then just into a simple connector. So that's all it is. And of course, so you'd have to obviously have a ground, so you could connect a ground to your board. And the idea is what you do is you'd go around your board and you could inject noise into your electronics and see if the electronics will misbehave. So, for example, it might suddenly do a reset. That would be a problem. And it wouldn't be anything you'd done wrong in the code or your logic. It would just be susceptible to a frequency. So what I can do here is, if I just sit the probe inside the search coil, back, whoops, like that, hold it there, and turn on the generator, we might see a spike. There we go, look at that. You see the spike there? And trust me, this says 500 megahertz, and there's 500 megahertz. I could move it. Okay, this says 660. And hopefully if I move that, about 660 it says up there. So here's another way. I'm not sure, I've not seen any cheap ways of injecting noise. Because it really does need to be at a very high frequency. The problem we had with the medical device I've been working on, it had a problem at 450 megahertz, where as soon as we hit that frequency by radio waves coming in, all the measurements started to go absolutely crazy. And there was nothing in the schematic or the data sheets that would suggest it would have that problem. And if you didn't know about it, you'd probably just see all your readings go crazy and you'd have no understanding as to what was going on. I have now fixed it. With a bit of work, I managed to fix it with 3 1 nanofarad capacitors. So all these problems, they are real, they do happen, but they are all fixable. Right, okay.
Stephen, I have a question.
Yeah.
Do you have to feed, would it be practical to just have like a white noise generator and see if that upsets the circuit? How important is it that you can dial in the exact frequency that is?
Well, 2 things. One, I'm not 100% sure as to how to simulate the levels you might see at an EMC. So for example, with something like a Raspberry Pi, you're looking, it has to survive 3 volts per meter. If it's a medical product, it's 10 volts per meter. How to simulate those sort of levels with this, I'm really not sure. So there's a small caveat. If you're just using white noise, which is essentially every frequency you can think of, how would you know which one is causing you, or which band is causing you the problem? And how would you then fix it? Because if you've got a problem, say, let's say 450 megahertz, that's a different capacitor solution to what you might have if you had a problem, say, at 1 gigahertz or maybe 80 megahertz. So,
but yeah, I was going to say maybe you could just put some capacitors in, and if it starts working, then you know you've fixed it, even if you don't know.
Well, that's very true. Because you've got to know that you've got a problem. Yeah, I mean, you could absolutely guess, which is not a bad solution. I mean, you'll probably find, because where do you put the capacitors? How do you fix it? There's the other question. So being able to sort of inject the right note frequency in gives you the confidence that, yeah, that solution has fixed the problem.
Well, how did knowing the frequency help you to know where to put your capacitors?
Okay, so
sizing them.
Right. Okay. Let me just change cameras, and I will draw an image. I'll show you. So this is potentially something of a black art. Excuse me. A bit hoarse. Right. Okay. So the problem we had was, this is the circuit. That's temperature sensor, T. And then this was a long cable. And then they went into an op amp. Okay, that's just, if you want to look at op amps, I think if you go to season 1, mid-season roughly, maybe 5 or 6, I'm guessing at that, there's a load of stuff in there on op amps. So this is an op amp here, RF, R1. And the gain is 1 plus RF upon R1. Okay, V out. So that was the circuit, and we had a problem at 450 megahertz. At that frequency, I'm kidding you not, suddenly the readings was going into an ADC and then a microcontroller and then over Bluetooth to a mobile phone. At 450 megahertz, the readings just went absolutely nuts all over the place. And there's nothing here to suggest why would that happen. So what I managed to work out, when you start trying to fix these problems, you put capacitors everywhere, a little bit like as you were just saying, William. So I added them here and here, and I put one here, I put one here, and I put one here across here as well, can you believe? And I injected the noise with the probe tip right here, using the generator I've got here. And yeah, I could see just a little bit of an influence. It wasn't anything like going to the EMC site, But I could see just a little bit of an influence going on here. But at other frequencies, it just wouldn't happen. So you put them everywhere to start with, and because it's about 450 megahertz, I know the sort of capacitor I need for that is going to be in the order of 1 nanofarad. If it was a much higher frequency, I might drop that to maybe, maybe 100 picofarads. If it was at the very low end of frequencies, I was seeing this problem, maybe I'd go for like a 10 or 100 nanofarads. It depends on where the problem is as to what sort of capacity you want. And then I just started taking them off one by one. So I took that one off to start with, didn't make any difference. I took that one off, didn't make any difference. And then when I took that one off, it made a bit of a difference. I was starting to see a lot of noise come back. So I put that one back. And we have spoken about active amplifiers before, active filters. So this is actually then operating as an active filter, and it took out some noise. But as soon as I started to remove this one or this one, things started to go back to their old games again. So then I put them back, and the problem still had disappeared. So my solution was 1 nanofarad here, and across this feedback here. All the other ones I then managed to take off, and well, just those two actually, and I got away with it remaining stable.
Mm-hmm.
Why it happens, I honestly don't know. There's nothing in the data sheets to say this is going to be susceptible. It just was.
Is there a chance that it was to do with the PCB or the equivalent?
It's a very good question. Yes. I mean, this cable length here, for example, must be about, what's that? Must be about 8 centimeters, maybe. Yeah, so also we found, I'm going to simulate it here, depending on what orientation the product was in, because when you do EMC, you test it from different angles. Every cube's got 6 sides, and you actually test it 4 of the 6. Don't ask me why it's not all 6, but they test 4 of the 6. And we found from one particular direction it was causing us a problem. And anything in line with the antenna, which is the camera, which is you, is probably then going to be the route in. And yeah, this cable. And yeah, we'll talk about more of this in our next, we'll talk about approval. But of course, you can have problems up to the 16th harmonic of a frequency. So if you took the wavelength of 450 megahertz, took a, is it quarter wavelength? Or halfway, the quarter wavelength, isn't it? You can take, and then if you divide that by 16, will you start to see a 16th harmonic come through the cable? Maybe. I didn't actually calculate that, but yeah, cable lengths, all sorts. And of course, as we're saying, as electronics get smaller and smaller in battery, I'm told EMC test site, they're starting to see more and more problems with battery operated products at really high frequencies. So there you go, word to the wise.
So is it just a rule of thumb, the size of capacitor you use in terms of compared to the frequency, or do you use 1 over j omega c?
I tend to use it as a rule of thumb, really. You know, it is a little bit of a black art. It is a little bit of a guesswork. It is playing sort of hungry hippos, where you whack one problem and then another one pops up. And think, well, what's going on here? So it's almost like trying to whack enough problems to try and keep the thing at a fairly, sort of, base level to get through. Yeah, sometimes there's no rhyme or reason to these problems. And again, come back to debugging. These aren't the problems that you think would exist. You'd go back and you'd think, well, what's happening in my code? Well, nothing's wrong with the code. It happens to be a susceptibility problem in the electronics. Okay, I've got one last thing I wanted to talk to you all about. So that's what I had for you on that.
Can I make a very quick observation?
Yeah.
I know you've run, but the T is a thermistor, isn't it?
Yes, it is. Sorry. Yeah.
Yeah. T could have been used as the feedback resistor, and then you get a nice linear relationship between the resistance of the thermistor.
Yeah, I didn't design the electronics as well as using it in the feedback. No, they couldn't have done that. Because this had to be far away from the rest of the electronics. So this lot could not have been where this is.
Okay.
However, what I think maybe in a future life, maybe using a differential instead, so any common noise gets cancelled out. That might have been another way of doing it, but there's no way anybody could have second guessed there was going to be this problem.
Oh, would it have been more? What if you'd have supplied the? I don't know if you could only have one wire to the thermistor, but maybe you could have supplied it with a current source and then measured the voltage you got, because the current source would perhaps be less susceptible to interference. I'm not sure.
Well, I came in quite late to the project. When a lot of the work's been done, people don't really want to go too far back, to the drawing boards, do they? They want to say, "Can we fix what we've got?" That's usually what happens.
I'm just speculating.
But yeah, I think maybe a differential amplifier might have been retrospectively may have been a more reliable solution. But the power of hindsight is a wonderful thing, isn't it?
Yeah. Well, I was really just addressing it in context of, if I had to design one of these, how would I do it?
Yeah, I certainly would not have done it like this. I think that's asking for trouble. I'm not saying trouble at 450 megahertz. I think from a noise perspective, it's asking for trouble. If you're trying to measure, small variances in temperature, it's also these are non-linear as well. So there's another issue. I think you just mentioned that, didn't you, William? The non-linearity.
Well, it is really the non-linearity resulting from putting it in a potential divider.
Yeah.
Even if in relation to temperature.
Yeah, exactly. Yeah. And sure, yeah, and there was, I could see on this circuit there's quite a noise problem as well. So, obviously the noise I could get rid of, through a bit of digital filtering. That wasn't the end of the world. But it's nice if it's not there in the first place, isn't it? Okay, look, last thing, got a couple of minutes. I wanted to share with you. So I'm starting to think about season 3. And this is what I'm thinking of doing. And I'd welcome any opinions, any thoughts. What I'm thinking, season 1 was very much about basic electronics. Season 2, that's this season, is really around microcontrollers, but maybe still, sort of broken down basic electronics, but thinking about it maybe from a microprocessor perspective. I'm thinking maybe season 3 starting in September of actually building something around the Raspberry Pi Pico, which I happen to have one here. So for those who live in Cambridge, we've got the Raspberry Pi in, is it Lineyard? That's what I still call it anyway. I think some people call it the Grand Arcade, but it's Lineyard to some of us locals. But if you pop in there, or I'd probably get these online. So this here is just a development board that you can plug these or solder in these Pico Raspberry Pi boards. These are like £3-4 quid each. So that they literally are uber duper cheapest chips. So what I'm thinking of maybe season 3 of maybe actually building something. So I'm starting to design a slightly different module board. So all the designs will be free, open source, online. You can download, send them off to any of the manufacturers, or you can just go into town and just grab one of these. The one which I've been looking at designing, I've just got some of the debug features which we've been looking at an hour ago. Another thing to slowly build up and actually make something. So I was thinking of doing vibration, which is accelerometers, because you can do tilt and all those good stuff. Temperature, just been talking about that. Sound proximity. Ruth, you mentioned light, didn't you?
Yeah, I just thought making what one can simply call a torch, but with lots of bells and whistles, like, you know, if you pick it up, it turns on, sort of bells and whistles. Or, you know, it's a torch that's using a multicolored LED or things of that sort.
And so what I was thinking of doing is exactly the same format as here, but it turns out I think we need about 7 of these on here. Can you just see that? Okay, just lighten up a little bit. That's better, isn't it? So look, your Pico goes just here, and then, you know, we can make tiny little boards just to drop in there. So I was going to do some designs. Everything, you can just download it, you know, freebies. And, you know, we could do a bit of analog co-processing. Certainly if you're going to do, you know, frequency analysis, sometimes it's better you can do some of that in analog and then send it over the ADC into these devices. But this is just an M0 plus in here. I think it's 2 M0 plus, if I remember.
Correct.
And a bit of data processing, and probably do it in MicroPython.
CircuitPython's better.
CircuitPython. Okay, right. I haven't heard of CircuitPython.
CircuitPython is Adafruit's update of MicroPython. And I say it's better because there's oodles and oodles, like hundreds of little bits of Python in the Adafruit repositories and elsewhere.
Okay.
To support lots and lots of different sensors.
Right. Anyway, that's my thought for starting in September. You know, maybe 9-10 sessions, similar to what we've done for the last 2 years. How does anyone feel about that as an idea?
Oh yeah, I think it's a great idea. Did you say we're going to come up with a specific project, or just?
Well, I don't know at the moment. I'm open to suggestions. Why, you know, I'll talk about it more in our last session next time. But I wanted to air it and see what you thought. Anything in particular, like CircuitPython? Are we going to build something? Maybe you've got a project of interest. So rather than being sort of, you know, the generic stuff, we can focus it on actual something which, you know, you can make, and it's not going to cost the earth to make it. That was where I was going with this.
Yeah.
Okay, everyone's gone quiet. Everyone's thinking that's a crazy idea. But, you know, I'm open to suggestions. You can always drop, you know, a note on email or meet up or make space on the Google group. But anyway, I'll probably talk about more next time. So I've been thinking about this for the last few weeks, and I've got a few half-baked designs on the computer at the moment. You know, looking at if we wanted to, for example, excuse me, wanted to use one of these. Oops, if I get that out. So in town in the Raspberry Pi shop, you can get the various displays. And what I found, if you have a look at these particular displays, they tend to use some generic pins. So whilst you want to be able to use the pins for anything you fancy, there is just about enough pins to be able to a tiny bit of GPIO and an I2C bus and an SPI bus. You can get all of that and an LCD screen. There it is. All operating off one tiny Pico. And I thought, yeah, that wouldn't be too bad for us to try and have a go at next year. Well, next season, I should say. Anyway, right, okay. I think
I've got a couple. Well, a thought, which is there is available on Tindy and Lectrons
Oh, yes, you
a
mentioned
thing
it.
called a Raspberry Pi stamp. LECTRONZ.
That's close.
So electrons is a thing a bit like Tindy, but it's been set up to give a bit more back to the creators than Tindy does. Anyway, so the point of this is that there's a thing called a Raspberry Pi stamp. It doesn't have, well, it's very, very, very comparable to the devices that you can get from Raspberry Pi Foundation. So the little boards you've just been looking at. Except that it actually has all of the Raspberry of the RP2040 IO pins available. Because the one you've just been looking at, it doesn't have all of them.
No.
There's in particular the ADC3, as in the fourth ADC input, is missing.
I built this on the RP2040, which is.
Oh yeah. It's, well, as far as I know, it's very, very compatible with the boards you've been looking at. It's also smaller. It's a 1 inch square.
Okay.
The downside is it's not so easy. It is possible, but it's not so easy to use it on a breadboard.
Okay. And what about, do you know anything about the availability? Because that's the other thing which I'm conscious of, you know, for season 3.
As far as I know, it's very available.
Right.
You know, that in terms of RP2040s, there's lots and lots available from the foundation, and you know they're just saying we've got lots of them. And Builder Party, who make the stamp, are, as far as I know, not in any problem supplying them. I mention this just as an interesting alternative thought. You know, obviously, if you've got a particular sort of form factor thing going on, then it's not going to work.
I'll have a look at that. A lot of it is about availability, because what I don't want us to do is go down a road when we discover we just can't buy stuff.
Yeah.
Whereas I know for a fact that, you know, the Pico, you know, it's super cheap, £4, £3. Interesting. I was quite curious that I think if you go to the shop, you can buy 5 for 15, or you can buy 10 for 30.
Right. Yes.
I was able to get 3 for £10 from the shop.
Sorry, say again, William.
I was able to get 3 for £10 from the Raspberry Pi shop.
Oh, it's 3 for £10. Oh, okay. So what I bought these last Friday, and I bought 5 for 15. So £3 each.
Obviously, some variability in supply, but anyway,
it's available. And of course, the other great thing about the, I don't know about the Raspberry Pi stamp that you mentioned, is the power supplies on here. So you can hook into the 3v3 power supply, which is very handy.
Let me Whipple. What's happened? Why is chat one of the things? Right. So I've just posted the.
Oh, there you go. Okay, I will look at that shortly.
That's on Pimeroni.
Oh, right, yes. So a lot of the stuff in the Raspberry Pi shop is from Pimeroni. I think these displays aren't they? Pimeroni, and guess what? So it's that is as well.
2mm pitch on the stamp. That sounds rather.
2mm, not 2.54.
Yeah.
So it's smaller. So that's not very compatible, is it, with breadboards?
No. As I said, it's not very compatible. The same company, Builder Party, do supply an adapter board if you want it to adapt. And there's also a carrier board which makes it look more like an Arduino something or other.
Okay.
Anyway,
I've got a few ideas. I'm working on it. I'll have some more thoughts, you know, in 4 weeks, which is our last outing for season 2. Season 2, so just before we go and put the kettle on everybody, it's Wednesday the 6th of July, and it's going to be on approvals. I could probably fill an hour with anecdotes of horror stories. In fact, a horror story which I will save for next time from last week from this medical product, a horror story. So I'll hang on to that one. Yes, it'll be more about stories and what can go terribly wrong rather than fixing things, I suspect.
Yeah.
Anyway, okay, so just what, 10 minutes over. Has anybody got anything else they'd like to add or ask about?
I'm going to be a broken record, but I really want someone at MakeSpace to get one of those mini. Oh, sorry. The spot welders that you used for batteries, you know, the little titchy ones. And I don't think there is one there, but and I'm not quite sure how purchasing works for MakeSpace.
I think you just suggest it to Ward Hills, right? And probably how much it is and where you get it from, and I think that's about the size of it, as far as I'm aware.
Yeah. Anyway, that was it.
All right, everybody. Thank you for joining. And note in your diary. And of course, I do send out emails for everyone who joins these, just as a little nudge. In fact, we're meeting up first Wednesday of the month. Okay, right. Time for a cup of tea. Yeah. Thank you.
Take care, all.
Bye, everybody.
Bye.